Rivers, the agents of change in the landscape. Rivers carving and shaping out countryside, carrying the debris of millions of years of wrestling with the mountains to form fertile coastal plains.
Can you guess the most common cause of death amongst the early settlers? Yes, it was death by drowning. Rivers had to be crossed on foot or by horseback in the absence of engineered access. A hazardous venture in this geologically young country with its many fast-flowing torrents.
But how do you bridge a river like this, that every time it rains can change course? You really have to allow for water crossing under anywhere. So the braided river systems of the Canterbury Plains need the longest bridges in the country. The colonial settlements could not, however, afford the luxury of two bridges, one for rail and one for road. So the way over was often shared by both, a system that works well when traffic flows are relatively light. And where you are halfway between the gorges and the plains, perhaps there's another way to economise on your bridge, but at the same time separate out the different types of traffic.
Of all structures in the landscape, a bridge makes the most emotive statement of what engineering is all about. It seems to me that an engineer in designing a bridge comes closest to being an architect in partnership with nature. But the beauty of form you see in a bridge is not just a matter of architectural style, it's a statement of forces acting and reacting and carrying loads across a gap.
The nature of the gap, the shape of the landscape, the type of materials and construction techniques available to the engineer all play a part in deciding what structural form the bridge will take. Of course, some bridges do not have to span rivers, but are there to cross the gap caused by past battles between landscape and water. The bridge engineer thus aims to achieve strength in design with economy in construction. The classic line of an arch bridge combines strength with grace. The sweeping curve between abutments looks right somehow. This Grafton Gully Bridge in Auckland was the first reinforced concrete arch bridge in the Southern Hemisphere. Not a bad effort for the early 1900s. The earliest arch bridges were built in stone, a strong and durable material that has left a living historic record of great bridge building achievements.
Travelling south from Oamaru on State Highway 1, this bridge from the top looks just like any other highway bridge. But how is it supported? Come over here and take a look from where I'm standing.
This bridge is supported by a series of classical stone arches. It's one of a number of lovely old bridges on this part of Highway 1. This one is 110 years old. Its designer was John Thompson, who hailed from Twizel in Northumberland.
The key to the strength of an arch bridge is in the abutments. They have to resist the weight of the bridge and the weight of traffic. Well, there's no doubt about strength for abutments here. Just look at those solid rock walls. Aha, I hear you ask though, how does one prop up an arch while constructing a bridge across here?
The use of steel simplified construction immensely. The new Kawerau Gorge Bridge here in central Otago replaced the original suspension bridge. Do you notice the similarity in form between these two bridges? the suspension cables curve down as they carry the bridge loads by tension. An arch curves up as it supports its loads and compression. They're in a way equals but opposites. And strong abutments are also the key to the strength of a suspension bridge.
This is the simplest of suspension bridges. Cables anchored firmly in each bank. Trouble with cables, they make for rather a flexible structure. But this is fine if all you require is foot access across a river. If the sides of the riverbank are not suitable for anchoring your cables, you have to dig a deep anchor block in the ground and then prop your cables up with piers. This bridge is still safe, but it's a bit shaky.
Road traffic needs a more stable platform than this. To stiffen the bridge deck, one solution is to use side trusses, supported by cables. Taken to their ultimate development, suspension bridges are the longest single spans in the world today. But in a rugged area like this, miles from anywhere, you need a bridging method that uses local materials which can be assembled from easily handled pieces. And in a young country needing rapid expansion of its lines of communication, truss bridges were the answer. Trusses combined lightness with strength and economy with ease of construction at remote sites. And the Public Works Department made good use of truss designs in pushing early roads and railways through. Truss bridges are still being built today. The Auckland Harbour Bridge is a good example. At each end, the truss supports the deck from below, and to allow ships under the centre span, the truss arches over, carrying the deck from above. This bridge also has some additions which illustrate a more recent development in bridge design, the use of box girder construction. The welded steel box shape provides strength and rigidity and an elegant slenderness. 2 lanes were added on each side, but they are really separate from the original bridge. All they share is the support of the piers. Using box girder spans, British designers and Japanese and New Zealand construction engineers turned one bridge into 3. Most of our recent large bridges have applied the box girder to their construction through the use of that favourite local material, concrete. Modern pre-stressed concrete designs enable engineers to precast sections like a kit set. Assembly looks deceptively simple as each section, strengthened and tied together with steel strands, is built out from supporting piers to form graceful, slender spans. But if you want to build a new access bridge over an existing very busy motorway, how do you prop it up without disrupting the heavy traffic flow? World War II Bailey bridges were built on one bank and launched out on rollers over the gap. Now today's civil engineers have borrowed the technique, as Ministry of Works engineer Alex Gray explains.
The bridge started in an excavation pit behind the abutment called a casting bed, and this is basically a very precise mould for fabricating 20-metre units of the bridge. And in front of the first unit was a steel snout called a launching nose, which is to assist in the launching process. After the first 20-metre segment had been cast and cured, this was then pushed out of the casting bed towards the first pier, and subsequent units were cast on the back of the previous unit. Although it was cast in segments, the actual bridge is structurally integral across the whole length. This is particularly important at Nowronga because the two bridges cross the active Wellington Fault. The bridges at Nowronga were the first of their type constructed in Australasia by this method. While we were building it, we had engineers from Australia come out and have a look at it. It's been used extensively in Europe. It was originally developed by Leonhardt and Partners, a consulting firm in West Germany. And as I say, a large number have been built in Europe. The Japanese, who have also got a fairly densely populated country, have done a number of bridges over there, and some have been done in Africa as well.
Looking at the Nowronga Bridge, it's a beautiful bridge. Do you get a sense of pride in being involved in a project like this?
Yes, I do. I think it's very satisfying to be involved in something which is obviously the end product is beautiful. I think that it's a credit to our designers that they've come up with such a fine line at Nowronga, and I think the bridge under construction at Fitzherbert is even better.
This mass of concrete and reinforcing steel is another section being prepared to be launched out, not over a busy highway, but a river. Here at Palmerston North, contractors are using the same equipment used at Nowronga to launch their spans across the Manawatu River. There's one more type of bridge to consider. This one is more than just a water crossing. Instead of passing water under it, this structure must hold it back. Probably no other engineering work impacts on the landscape more than a hydroelectric project. Great strength is required to hold the water back and allow the surplus to escape safely. Here at Clyde on the Clutha River, construction of a massive concrete plug across the valley is well underway. It's the sheer weight of that concrete that will hold the water back. Notice how the huge concrete blocks have been notched into the sides of the valley and the riverbed to make the structure watertight. It's hard to believe that the ancestry of big schemes like this goes back to the gold mining era, near the turn of the century. This Pelton well generator system here at Kanieri Forks in Westland was built to supply power to the Ross Goldfield in 1909. The local power board operates it now, the oldest community hydropower scheme still operating in the country.
Crumbling concrete and rusting iron. That's all that remains of what is thought to be the first community hydropower scheme in the Southern Hemisphere. Look at this. It's the remains of the old generator. And over here we have the old turbine casing. You know, this really ought to be a national monument.
Reefton was certainly the first town in New Zealand to be lit by hydroelectricity, if not the first in the Southern Hemisphere. This was in 1888, only 6 years after Thomas Edison's scheme for lighting New York commenced operation. In 1903, the government turned hydroelectric power development into a growth industry. The Lake Coleridge scheme was the state's first big project. It began an era of dam building that continues to the present day. Within a year of commissioning this project, demand exceeded supply. Today, consumers and industry still keep up the pressure for additional power generation. Fortunately, New Zealand is a hydroelectric mecca, with its ample rainfall and geologically young and active river system ideally suited for generating power. The country's most intensively developed river system for hydropower purposes is the Waikato River. In 40 years from the 1920s, 8 major power stations have been built between Lake Taupo and Hamilton. And more recently, the Tongariro Power Scheme has been developed to collect water from all over the central North Island volcanic plateau. What made the Waikato such an ideal river for power production? For a start, it was the volume of its flow coming as it does from all over a large part of the central North Island. Also, it has carved its way deep into the volcanic ash and rock of the central plateau, so providing a long, narrow gorge ideal for plugging with a series of dams.
But the geology of the Waikato River Gorge set a quite different challenge to the dam builders than did the rocky gorges we saw earlier in central Otago. And it was here at Arapuni in the 1920s that the first major dam on the Waikato began its checkered history.
The Arapuni project was the most ambitious work attempted in New Zealand to that date, and generated much controversy as to the competence of New Zealand engineers to handle it. The dam here is just a simple concrete plug wedged in against the sides and bottom of the gorge with its sheer weight holding the water back. And that was where the first problem lay. The rock in the sides of the gorge was much softer than had been expected. And when the storage lake was filled, the dam leaked around the edges. That was only a minor problem to what happened next. A headrace canal carries water from behind the dam along the top of the bank and drops it down through the penstocks buried in the cliff to the powerhouse in the gorge.
Well, 18 months after the headrace was filled with water there, a large crack opened up along its length parallel to the riverbank, and the whole massive side of the gorge, including the powerhouse down there, tilted out slightly toward the river.
With some alarm and much haste, the engineers shut the power station down, drained the headrace, and with considerable relief watched the hillside settle back.
So, what went wrong? Well, the headrace is located in an old river channel that was formed tens of thousands of years before the river cut its current gorge. That old channel, in fact, made an ideal approach canal to bring water to the top of the penstocks. However, with the river flowing in it again, water seeped deep into the ground, the volcanic soils swelled, and the whole hillside moved outwards.
The solution? 2 years hard work to line the headrace channel and dig dewatering drains deep into the rock along the bank of the gorge. The end result? A successful hydro scheme that has performed most satisfactorily ever since. Where you have a narrow river valley, a concrete dam can economically plug the gap. But for a wide river valley, a different technique is required.
The principle of an earth dam is to fill across the valley with carefully compacted rock and gravel and sand until you have enough weight of earth to hold back the lake of water leaning on the upstream face. Now remember how at Arapuni water pressure seepage into the soil caused problems? Well, the same would happen here unless specific design precautions were taken to prevent it. So an earth dam is given a watertight core. Here at Benmore, a band of clay gravel is held in place by the weight of gravel on either side, so as to keep the upstream water back. It's notched into the original country to provide a seal all around. And on the downstream side, a network of drainage pipes collects any seepages and rainwater, keeps the toe of the dam dry. If, as has happened with some overseas dams, water builds up on this side, the face of the dam could give way. The watertight core could thus be weakened and the dam eventually fail, with disastrous results to communities downstream.
When commissioned in 1965, this had been the largest earth-moving job in New Zealand. Behind it lay the largest man-made lake in the country. The weight of water trapped behind the dam actually caused the Earth's surface to deform slightly, causing minor earth tremors in an area where few had been recorded before. Notice the very important component of any dam, the spillway to pass flood flows. The spillway is doubly important on an earth dam. The reason? Overtopping of the dam would quickly scour away the earth fill. So the spillway must ensure that the largest ever possible flood can be accommodated. Just as Arapuni uses a short length of canal to carry water to its powerhouse from the lake behind the dam, further up the Waitaki River beyond Benmore, we find the same principle being used on a massive scale. Instead of dams to raise the water to provide energy for power, huge canals are used to shift lake water across country so it can be dropped over the ridges into a power station. And not just one power station, but a whole series, so the water is used and reused again. This has been a huge undertaking, even by world standards. This canal is 10 metres deep, 70 metres across. You could sail an inter-island ferry and hear no bother.
But it's not only dams and canals that are used to control water for hydroelectric power purposes, there are also tunnels. And buried deep in the mountains over there is New Zealand's biggest ever tunnel engineering project. There are no roads in here. The only way you can get to Manapuri Powerhouse is by boat.
The powerhouse tour buses never get out of second gear. Year-round, they take thousands of visitors on the pilgrimage to the heart of this project. The tourists don't see everything on their spiral journey down the access tunnel. Hidden within the rock walls are penstocks and cable shafts. The tail race tunnel has been bored 10 kilometres through the mountains to an outfall at Doubtful Sound. Within this cathedral-like structure, you can feel those great powers of nature vibrating underfoot. But what happens when engineers lose control of the powers of nature? On December the 24th, 1953, northbound Express 626 left Wellington for Auckland, full with Christmas travellers. Its destination was never reached. In our next program, we examine the engineer's response when things go wrong.